BMW just unveiled its newest humanoid worker, but what can it do and how much will it cost? Today on AI News, we're taking a closer look at several of the latest AI breakthroughs, starting with BMW's newest robot. This is the AEON from Hexagon Robotics, and BMW chose this robot first for its hardware. So it stands at 165 centimeters tall, or about 5 feet 5 inches, and it weighs 60 kilograms, or about 132 pounds, which is a realistic human-like proportion, and throughout this robot's body, it features 34 degrees of freedom. And you can see here that it moves on a wheeled base, forward, backwards, and can pivot. And the speed here is about 2.4 meters per second, or 5.25 miles per hour. And in terms of manipulation systems, it features bionic hands, which are equipped with modular gripping tools and scanning systems. And it can carry 15 kilograms of weight short term, or about 33 pounds. But in terms of constant carrying capacity, it reaches up to 8 kilograms of load, or 17.6 pounds. And to power all of it, it runs on 2 auto-swapping batteries, each lasting up to 4 hours, so that when one dies, the other can take over with zero downtime, continuous operation. And this powers its 24 sensors, which include 12 cameras, peripheral, front-facing, rear, as well as AR heat detection, which is all powered by this robot's onboard AI software. But where this robot really stands out is in its AI. So it houses 3 specialized onboard computers. 1 is a general engine, and 2 are dedicated AI processors for edge autonomy and mission reasoning. And it's all running on NVIDIA's Jetson Orin, but trained primarily in simulation using NVIDIA's Isaac Sim and Isaac Lab. And it also learns from human demonstrations via NVIDIA's Isaac GR00T Foundation model, as well as mimic tools for synthetic motion data. So this is what BMW calls physical AI. And their first test deployment was in December 2025 in Leipzig, Germany. But they're moving on to a second deployment on the factory floor this April 2026, with a full pilot phase happening this summer in 2026, with a focus on the robot doing high voltage battery assembly as well as component manufacturing. And when it comes to this robot's cost, it's not for sure yet, but there are rumors that they're shooting for around a $20,000 price range. But how much would you pay for this robot? Meanwhile, robot movements are getting extreme thanks to OmniXtreme, which is breaking the generality barrier in high dynamic humanoid control. Basically, OmniXtreme's goal is one unified control policy that handles the full spectrum of dynamic movements. And here are the 3 stages while I show you this robot doing its moves. So the first stage is pre-training, and this builds the foundation. So they train a unified base policy using something called dagger-based flow matching. So in simple terms, they take multiple motion tracking experts and aggregate all their knowledge into one base model. So you can think of it like learning to walk, run, and balance from different coaches, and then combining it all into one athlete. Then there's stage 2, which is post-training. This is like a reality check. And it's interesting because first they freeze the base policy entirely and train a separate residual policy on top of it. Then that residual policy is optimized under heavy domain randomization, meaning that they throw every possible real-world variation at it in simulation. But the key innovation here is its power safety regularization, which is the system that actively penalizes excessive negative joint power. And it matters because during fast dynamic motions like this, joints can absorb dangerous amounts of energy that could damage the robot or even hurt somebody standing nearby. Furthermore, they also model realistic motor characteristics like torque speed limits and actuator nonlinearities so that simulation actually matches what the hardware can do. And this minimizes the sim-to-real gap problem, which brings us to stage 3, deployment, which is all onboard and real time. So the entire inference pipeline runs onboard the robot in real time. It means no cloud, no latency, and this enables robust as well as agile control in physical environments without depending on external compute. And this mainly matters because of safety, where this approach specifically engineers against the robot hurting itself or others during its movements. And while OmniXtreme is solving how robots move their whole body, there's an equally important problem at the other end of the scale, which is how do robot hands actually grip things precisely? Because even the best vision language action models and grasping pipelines still fumble at the last step. The robot sees the object, plans the grasp, reaches for it, and then the final grip is slightly off. And even though a few millimeters of error doesn't sound like much, in long horizon tasks where you're chaining multiple actions together, these small errors compound fast. And this is what researchers are calling the last mile problem in dexterous manipulation. So now enter TacRefineNet, which is a framework that throws out vision entirely at the refinement stage and relies purely on touch. Using multiple fingertip tactile sensors, the system iteratively adjusts the robot's grip based on what it feels, not what it sees, and then aligns the object to the exact desired pose. In fact, the architecture is a multi-branch policy network that fuses tactile inputs from multiple fingers along with proprioception, which is the robot's sense of where its own joints are in space, and it uses this to predict precise control updates in real time. Then, in terms of training, large-scale simulated data from a physics-based tactile model in Mujoko was used and then fine-tuned with a small amount of real-world data, and that sim-to-real combo significantly outperformed simulation-only training. So what makes this really impressive is the range of what it can handle. Specifically, they tested across 16 distinct pose pairs covering pitch, roll, and positional adjustments, and the system reliably nailed them all. In long horizon tracking experiments where the object's pose was continuously perturbed throughout the sequence, TacRefineNet kept adjusting and maintaining the target grasp. And when they tested on completely unseen objects with different shapes and thicknesses, the policy still generalized well, particularly for roll adjustments on flat objects. And to the researchers' knowledge, this is the first method to achieve arbitrary in-hand pose refinement using multi-finger tactile sensing alone. So no vision, no external cameras, just touch. Anyways, here's some more video showing robots doing breakdancing moves. Anyways, make sure to like and subscribe for more of the latest in AI news, and check out this video here.